Hello. In today's Principles of Computer Security lecture, we are going to be looking at Advanced Encryption Standard. In the previous week, we briefly discussed about block ciphers and the data encryption standard. And as a continuation from that, today we are going to be focusing on Advanced Encryption Standard, or AES. So even when we were discussing DES and block ciphers, we sort of identified towards the end that DES has some significant shortcomings, and particularly towards the mid to late 90s, there have been a number of attempts, a number of successful attempts in terms of breaking the cryptography. So the cryptographic attacks on DES were there. So then that in itself proved that there was a replacement needed. And we also briefly touched upon using the approaches of double DES and triple DES and how that can improve the security of those of that particular encryption mechanism. But the challenge with triple DES, for example, is it can be significantly slower, particularly when it is implemented as a software algorithm, and also it has the disadvantage of having small block sizes as DES is. So mid-90s, in 97, the National Institute of Science and Technology, or NIST, in the US issued a call for new ciphers as a replacement for DES. So there were 15 candidates accepted for consideration, and of those 5 were shortlisted, and in October 2000 a particular one called the Rijndael was selected as the Advanced Encryption Standard, or AES, and then it became a standard in 2001, and since then it has become the de facto standard for encryption in many applications. So even though DES may still be used in certain legacy applications, other than that, AES has become the de facto standard for data encryption in many places. So when talking about AES, there were a number of key criteria to consider when AES was selected, or a particular algorithm was selected as AES, or the Rijndael was selected based on these criteria. So security was a key concern. So given it is an encryption standard, security was a paramount of paramount importance. Then cost. When we say cost, it is about the computational cost. So that is how efficiently that we can achieve a higher level of security. So it's not good enough to have higher level of security, but also it should be efficiently computable. The computation should not take a long time, a lot of computation power. So we don't want that. So that is also an important factor. Then the particular algorithm and the implementation factors are also important there, whether that can be implemented in hardware, whether that can be implemented in software. So those are also things to consider. Then also, when considering this implementation, then are there any sort of attacks that can happen on the implementation itself? So it's not just the algorithm, but also the implementation has to be done in a secure manner. So that is also a factor to consider there. Then other factors such as flexibility in encryption, flexibility in decryption, and these are also things of importance when a particular algorithm was chosen as the advanced encryption standard. So that is the Rijndael algorithm. So when we talk about the AES Cipher or the Rijndael algorithm, the Rijndael Cipher, it is developed by 2 scientists from Belgium. Even though it became a US NIST standard, it was submitted by 2 scientists from Belgium. And in terms of keys, it supports 128, 192 or 256 bit keys with 128 bits of data. So the plain text could be 128 bits. Using one of these keys, a cipher text of 128 bits would be produced. So it is a symmetric cipher. So that is a plain text, an equivalent length of cipher text would be produced. And this is significantly different from the Feistel cipher. That is, it is a iterative cipher, and it is done in the data is considered in the form of a 4x4 column matrix, 4-column matrix, and of 4 bytes. So the hence forming the 128 bit data. And the all the process throughout that we will discuss later will consider this 4x4 block as the basic unit of operation. So that is the state of data that will be considered there. Then some of the main design concerns are it is resilient or resistant against all the known attacks. It can be implemented on CPUs and on devices with speed and compactness. So it doesn't have to be so complicated in terms of its implementation, and it has a simple design. So these are the main factors about the Rijndael cipher or the AES cipher. So when we think about the AES cipher, the main factor to remember is the data will be split into a matrix like this. So if we have 128-bit data, it becomes 16 bytes. So we have 16 bytes, and those 16 bytes will be represented as this byte 1, byte 2, byte 3, and so on. So and byte 16. Then again the key itself will also be expanded into array of words. So then again all the operations will be done on these matrices and arrays. Then in terms of the rounds of operations, that will depend on the length of the key. So if we have a 128-bit key, it will be 10 rounds. If we have a 192-bit key, it would be 12 rounds. And if we have a 256-bit key, we will have 14 rounds. And of those 10, 12, or 14 rounds, the first or the 9, 11, or the 13 rounds, except for the last round, they will go through the a similar process, and the last round will be slightly different from the other round. So that is a broader overall AES structure. Then when we think about each of those rounds specifically, we will start with the key expansion. So the key expansion is where we would take the existing key and we will derive the round keys using the Rijndael key schedule. So that is, we will have a key 128 bit key, for example, and we will start with that key, and then we will expand that into various round keys, say 10 rounds, 12 rounds, or 14 rounds depending on the length, and we will produce those round keys. Then with each of those initial round keys, we will take the round key, and each byte will be combined with the round key using an XOR. So the round key will be combined with each of those bytes. Then for each of those bytes, we will do substitution of rows, we will do shifting of rows, we will do mixing of columns, and then we will add the round key again. Then except for the final round, The only difference in the final round is we will not do the mixed column that we would have in other rounds. So this is the overall high-level process of AES. So we will have key expansion, initial round, other rounds, then the final round. So if we look at AES encryption process, so we will start with the plain text, and then that plain text will be converted into the input state as this matrix. Then as you can see, all over this place, it will continue as this matrix form in all these processes. All the operations will be carried on this matrix process or the array process. Then we will do the initial transformation with the round 0 key. Then we will go into round 1 and up to round n-1. It is the same process, and except for the final round where we have 3 transformations. All the other rounds will have 4 transformations. So the key expansion will be providing the round keys for each of those rounds, and then finally we will produce the ciphertext of the same length as the plain text. So that is the basic AES encryption process. So if we look at the AES structure, the structure of the AES cipher, it is an iterative cipher rather than a final cipher, which DES was. And the key is expanded into the array of 32-bit words, and 4 words will form the round key in each round. So 4 words will be taken as a round key for each round. And 4 stages will be used in each round, except for the last round, which will not have the mixed column stage. And the add round key stage is the only one that will use the key. Other parts will be only about substitutions and permutations. So as we discuss about SP network substitutions and permutations, and how we can bring in confusion and diffusion using substitution and permutation. So again, in AES, we are getting those things in by doing these operations, the substitution, shift rows, and mixed column operations. We are getting those things. When we consider decryption, for example, the encryption and the decryption is essentially the reverse process, and it will use the same keys but in the reverse order. So the last key used in the encryption process will be used as the first key in the decryption process. So other than that, it is again a similar process going from plain text to ciphertext, and then ciphertext to plain text. The operations are done in the reverse order. So again, we can see that a bit in a bit more detail here. So what we would start is we may start initially with a cipher key, and that key would be sent through a key expansion, and a number of round keys will be produced. And for the plain text, again, initially the round key will be added as the first round. Then for the first round, we will go through first round to the one before the last round. We will go through the stages of substitutions, shifting rows, mixing columns, and adding round key. And for the last round, we will not have the mixed columns, because at the very last column, mixing is just going to give an additional mixing of columns. It doesn't affect the cipher in any way. It doesn't affect the ciphertext in any way, rather than additional jumbling of mixing of those columns. So it is not a state that is needed. So that is the reason why the last operation or the last stage does not need a mixed columns. And in terms of the decryption process, it is essentially the reverse of the operations in the same manner. Now let's look at each of these individual states in a bit more detail. So if we take the substitution box or the substitution state, for example, in substitution, it is basically a simple substitution for each byte. So again, we will have the state in the form of the 4x4 array, and the substitution will happen for each of these bytes. There will be a substitution. So again, we will have this will be done using a comparator or a substitutor, and each of these states will be done in a, so we will go through each of the columns and then we will do substitution for each of the bytes. And the exact substitution transformation will be done in what is called this, inside this Galloway field, which is not, we are not going to expand into that topic area today, but the main thing to remember is it is designed in a way to be resistant to known attacks. So that is the main aspect of this particular substitution method. So what will happen is, for each of the bytes of the state, it will go and it will select from a existing lookup table, and that will produce a substitution there. So if we have, this is the input text, the substitution, after substitution, an output text will be produced of the same size, but this S box or the substitution box or the lookup table is something that is designed in a way, in a non-linear manner, to produce outputs that are much complex to derive at otherwise. So as the first step, we do substitutions. So we take each bytes in our matrix and we substitute each of those bytes with different values from the substitution box. Then after that, the next stage is called shifting of rows, and this shifting of rows happen in this order. So the first row, nothing happens in the first row. The second row, we will shift one byte in a circular to the left. So we will go one byte in this order. So we will take shift one byte this way, and the first one will come as the last one. The third row, we will again shift left, but now we will do 2. So the 2 will come back here. And the fourth one, technically we do a 3 byte shift, or essentially we can also say that we are doing shifting in this direction by 1 byte. But anyway, we can call that the fourth row is shifted 3 bytes to the left. Then when we talk about decryption, the shifting happens to right. So that's the main difference in shifting rows. For encryption, we shift to left. For decryption, we will shift to right. Then again, what this produces as a result is again the same sort of state of a 4x4 matrix. So again, we will have the same thing as a result of this. So again, this is the example. So shift the first row, nothing happens to the first row. Shift 1, shift 2, and shift 3. So again, the input is a matrix and the output is a similar type of a state matrix. Then the third operation that we would do is what is called mixing of columns. So here what we would do is we would take each column separately, and each column will be replaced by values. Each of the bytes in those columns will be replaced by values that is dependent on all the 4 bytes of the column. So all the 4 bytes of the column, that those values will impact on what is the replaced value there. So we will effectively do what is called a matrix multiplication in a Galloway field or GF field, which is the main thing to remember, you remember here is, say, for example, when we say a Galloway field of 2 to the power 8, what we have is we will have a 8-bit value from 0 to 8 ones. So, and all the possible values in between that. And all the operations done in this field, the main point is they will produce, such as this prime polynomial multiplication and so on, will produce a result in the same field itself. So that is, even when we are multiplying, the result will be within the same range as we originally have. So that's the main thing you remember here. We will do matrix multiplications and the results will be again still in the same state, or will be within the range of the same state. So what we would do is we would take each column, and each column we would multiply by a particular matrix, and we will do a matrix multiplication, and that would produce the replacement column for that. So again, we'd start with the state and we would end up with a similar size state. So it will still fit within the same range. So when we consider these Galloway fields, the main thing to remember is this polynomial matrix multiplications is, the main thing to remember is whatever the multiplications or operations we do, the resulting value would still be within this particular field. It will still remain within this field. So any additions, any XORs, any multiplications that we do here within this field will still be within the range of this range of values. All the outputs will still be within the range of value. So that is the main thing to remember about this AES arithmetic here. So with mixing of columns, what we have is we will again, so as we explained, we will take each of the columns and we will produce a replacement column or replacement value for each of those bytes in the columns, which are dependent on the existing values of the column, all the different bytes of the column. Then the decryption will do the inverse of this matrix operation, use the inverse matrix to do the same operation, and we will use what is called the polynomial matrix multiplications or multiplied modulo operations. The details of these arithmetic operations is not the main concern for today's lecture, but it is something that we can discuss later on as well. But that is the main aspect of this mixing of columns. Then the last operation, the fourth operation, is the adding of the round key. So we will take the XOR, the round key. We will produce the round key, and we will get the round key for that particular round, and we will XOR that, and we will get the, again, we will get the same state, or in the same state, the value for each of those bytes. So the again, the decryption is identical because it's an XOR. It is automatically inversed there, and the main point here is this is designed to be as simple as possible without significant complexity, but still keeping up with the requirements of security. So we will take the state, we will XOR that with the round key, and then we will produce a resulting state there. So this diagram shows a detailed overview of an AES round, a 4-stage AES round. So what we have here is, we would start with a state. Then we would go through the substitution box. So for each of those bytes in the state, we will produce a substitution value through the substitution box. Then as a result, we will again come to another state. Then that state, we will do the shifting operation, shifting of rows in different order according to which row they are. We will do shifting of rows, and then from there we will produce another state. So that state, after shifting of rows, we will use that in our mixing of column operations and produce again another state. Then that state is where we would add our round keys. So we would add our round keys to the state produced from mixed columns, and that would produce the output for the round. Then that would go to the next round and onwards. So the main stages are the substitution bytes, the substitution box, shifting of rows and mixing of columns, bringing in the diffusion, and adding of the round key. So this adding of the round key is the only part that is a cryptographic operation here. Others are substitutions and confusions. One of the important operations in AES is the AES Key Expansion. So that is, say if we have a 128-bit key, which is a 16-byte key, then we will expand that into either 44, 52 or 60 32-bit words. So we are expanding that into a significantly larger array. So we will start from a smaller key, and then we would produce a larger key that can be used as a number of round keys depending on how many rounds we are going. So again, there is a particular process to go through AES key expansion. So we'll start by copying the key into the first 4 words, and then we will go through a loop operation, and using this operation we will produce a much higher length of words as the output there. So that is what we would use as round keys there. So for example, you can easily observe in the case of 10 rounds, we would need 11 keys, each keys being each 11 round keys, and each being 4 words. So or similarly, we may require different lengths of words for each of the different number of rounds. So that is what is being produced in a AES key expansion. The main thing that we will try to achieve when we are doing the key expansion is it should be resistant to known attacks, and they should also provide a significant level of security requirements, such as knowing part key is inefficient to find many more keys, or invertible transformations. In terms of performance, they should be faster on many different CPUs, using key bits to diffuse them, having non-linearity so that it cannot be done, any sort of cryptanalysis cannot be done, but it is also simple in terms of its simplicity is also an aspect there. So it has some different requirements in terms of this key expansion as well. So here we have an example of an AES key expansion. So what you can observe here is we would start with a number of words, and then we would go through a number of rotations, and then we would produce a different set of words. So that is the key expansion process, an example of AES key expansion. And here again we have an example of an AES encryption. So we start with the starting round, and using the particular round key we produce different outputs of each of these stages. So again this is just an example to illustrate. Then one of the things that we discussed previously in terms of DES as well, that Avalanche, so that is if there's a smaller change in say the ciphertext or the plain text, rather the plain text or the key, there's a significant change in the ciphertext. So here again this example shows that there is a 1 bit difference, and then the 1 bit difference after 10 rounds becomes a 58 bit difference. So it is a significant number of bits are changed when a single bit changes in the initial text. So again that is what we get in Avalanche. So that is smaller changes in the plain text or the key will result in a significant change in the ciphertext. So then when we think about the decryption in AES, AES decryption is not essentially identical to encryption, but certain steps are done in the reverse order. So the main reverse order is we will do add the round key first, then or rather we will add the round key, the initial round key first, but then the stages of mixing columns, then shifting rows, then substitution will happen in that order. So we will go through that in the reverse order. So each of those rounds will happen in the reverse order, and the use of keys will also be done in the reverse order. We will take the keys in the reverse order as well. Then when we think about the implementation of AES, one of the design criteria was that it can be implemented in slower CPUs or without requiring a lot of hardware or software capabilities. So one of the aspects of AES is it can be implemented on a 8-bit CPU, and that is enough to do all the required operations of substitutions, shiftings, round keys and so on can be done in a 8-bit CPU, and it can be even more efficiently implemented in a 32-bit CPU, and in present day that is a fairly common use case in sort of many computing applications, and that is one of the things that, and one of the main things that we would observe in many situations is that AES is available as a hardware level implementation in many CPUs, including many general purpose CPUs such as Intel's or AMD's and so on. Many of them, or at least some of the CPUs from these manufacturers have some AES capabilities implemented as part of the hardware itself. So it again is more efficient when we are using AES in this context. Then when we think about security of AES, AES was designed after DES, so a number of issues that were already known were DES were in a way addressed when AES was implemented. When we think about, for example, brute force attack, anything is possible in a brute force attacks, but it is much more complex or much more difficult than DES because it has a much larger key. Then statistical attacks, again, there have been a number of attempts to do statistical analysis attacks of ciphertext, but most of them have failed so far. And then differential and linear attacks, again, as of yet, there are no known such attacks on AES. But again, with anything on in sort of computer security, things can change with different computing capabilities and so on. This may change in the near future as well. So that's all for today's lesson. We have looked at AES and how the Rijndael cipher, the AES cipher works, the main steps in terms of the rounds of encryptions, and also key expansions and decryptions as well. And we also briefly touched upon some of the different aspects of AES. I will also share some additional resources along with this lecture that you may refer to get a better understanding of AES, and some examples and some tools that you can try out. Then other than that, if you have any questions, any doubts on this, please let me know through our usual communications or LMS, and I'll try to answer them to you directly. Then until next time, when we will be looking at public key infrastructure and so on, keep an eye out for some additional resources that will be posted along with this lecture, and see you next time. Bye.